Okay, good morning all of you. Any questions from yesterday's class? And there is one question related to this size of the beam, that is width and depth. Please note that width and depth is going to, even though in the example or the problem that we looked at, we assume some combinations of B and D such a way that they meet our requirements. But in reality, this B and D are going to be governed by the other members and other constraints. Okay, so it's not totally arbitrary. So at this stage, that is what I can say. Once you understand the entire structural system, other sizes of columns and beams and other things, please note that the width of the beam sometimes needs to match with the width of the column and other things. Okay, so it's not totally arbitrary, but it's going to depend on, these dimensions are going to depend on some other things. So you need to keep that into, or you need to take that into consideration while designing. Okay, so with that, let me start today's class. So any question from yesterday's class under reinforced section, or a beam which is deeper than a balanced section? So let me recap the important points related to this under reinforced section or a beam deeper than a balanced section. The stress in the extreme fiber in concrete is going to be less than the permissible stress in concrete. Okay, so that is one of the important points. The other point is you need to solve like a cubic equation to get the neutral axis depth, and also the area of steel can be obtained by considering that the steel is going to reach its permissible limit. So area of steel is given by this once you get the neutral axis depth. Okay, so that is another point. The other point is to calculate this cubic equation. You can make use of any of the iterative methods, or you can solve it by trial and error. And also we looked at one approximate method where you can skip this or you can bypass this solving this cubic equation to arrive at the area of steel by taking the depth as per the this beam which is deeper than a balanced section, the effective depth corresponding to that. But this Leverhulme factor, you take it as for a balanced section. So that gives you an approximate value for calculating the area of steel. This is what we looked at. But this approximate procedure or this approximation is good for beams when the effective depth is not larger than, or the effective depth is not more than 20% of that of a balanced section. That is what is given here. When D is larger than the balanced section depth by more than 20% or more, some steel can be saved by using the exact procedure for calculating the Leverhulme distance or the Leverhulme factor. Okay, so any questions here? So now let's, if there are no questions, so we looked at two types of sections. One is balanced section. Next one is a beam which is deeper than a balanced section, and that is what is under reinforced section. And next one is over reinforced section, or a beam which is shallower than a balanced section beam. Okay, and again, what kind of, under what situations you are going to encounter this kind of things? Beams shallower than a balanced section. Okay, so let's read this. It is rarely feasible to reduce the depth below the balanced depth by more than possible 10%. Okay, unless compression steel is used First of all, why this balance, this beam which is shallower than a balance section size or depth, why it is required is under certain situations where you have some constraint on the depth, like you need to have like clear space below the beam should be more under that situation, or when the ceiling height, if you want it to be more, then you need to go for this kind of beams. Other architectural considerations are going to dictate when this situation is going to happen. Okay, so we will not be having flexibility to design it with the depth corresponding to balance section. So we need to adopt a beam which is shallower than a balance section, whatever depth that is required for a balance section. So now let's see this. It is rarely feasible to reduce the depth below the balance section depth by more than 10%. That you need to keep in mind, unless compression steel is used. This means if you are using compression steel, then it's going to become doubly reinforced section. And so far what we did is for doubly reinforced section, you learned how to do analysis. And now we will see how to design a doubly reinforced section later, okay? But at this stage, we will not take this option, that is providing compression steel in today's class, okay? So with whatever depth that is under the constraints, whatever depth we need to adopt, using that depth, how to proceed with, we will see in this today's class. So it is rarely feasible to reduce depth below balance section depth by more than 10% unless compression steel is used. Reduction in depth greatly increases the steel requirements and makes this uneconomical, except for very small deficiencies in depth. First of all, this section which is shallower than a balance section, it is, we will see in a while how the, even as a part of your structural engineering lab course, you will be seeing or experiencing how the beams which are designed as over-reinforced beam, how their behavior is going to be, and how the beams that are designed as under-reinforced beams, how their behavior is going to be. You will be experiencing that. So usually we will not recommend you to adopt this kind of over-reinforced section, because that leads to a brittle failure. Okay, and at the ultimate load, concrete is going to reach its permissible limit first. So it's not advisable to do design this kind of over-reinforced section, but still for for completeness, we will see, or in some cases we may actually end up in this kind of sections. So for completeness, we are learning this. Okay, so the reduction in depth greatly increases the steel requirement. So when you are making, or when you are going for a beam which is shallower than a balance section, it not only it's going to be expensive in the sense steel requirement is going to be more. Please note that the cost of steel is going to be much higher than cost of concrete. So when the steel requirement is more, then it's going to be uneconomical. Okay, why steel requirement is going to be more, we will discuss in a while. Okay, so it's not economical except for very small deficiencies in depth. So now let's understand why steel requirement is more and other things. First of all, the beam is shallower than a balance section. Okay, so if beam depth is, effective depth is smaller than a balance section, so your lever arm distance is going to be smaller. Your lever arm distance is going to be smaller. So for the same amount of moment, for the same moment carrying capacity, the lever arm distance is going to be less for a beam shallower than a balance section or over reinforced section. So if lever arm distance is small, you go back and see these the two equations which are connecting the applied moment with the stress in steel as well as stress in concrete. Let's see the first equation, or the first with respect to concrete. M is equal to half, you recall the relation, M is equal to half sigma prime CBC multiplied by B times N multiplied by the lever arm distance. So when the lever arm distance is smaller, and for a given moment, your sigma CBC prime, stress in the extreme fiber in concrete, is going to be is going to be more, because the stress M divided by half B times N times lever arm. So lever arm is smaller, in the denominator you have a smaller quantity. So your stress in concrete in the extreme fiber is going to be higher. So that is how the stress in concrete is going to be higher for a beam which is shallower than a balance section. See, applying similar kind of reasoning for steel as well, using the relation M is equal to sigma prime AST, sigma prime ST multiplied by AST multiplied by lever arm distance. If you want sigma prime ST, it's going to be M divided by AST multiplied by lever arm distance. When lever arm distance is small, which is in the denominator, your stress in steel is going to be higher. So this is the reason. This is the reason why for a beam which is shallower than a balance section, stress in concrete as well as stress in steel are going to be higher. Okay. So how to bring down the stress in the concrete as well as stress in the steel to their permissible limits. Stress in concrete, let's discuss how to bring it down in a while. Stress in steel can be reduced by increasing the area of steel, by providing more steel than what is required, or marginally you can add some additional steel and bring down the sigma prime ST to the permissible limit. Okay, but to increase to reduce sigma CBC prime, which is the stress in concrete in the extreme fiber, to reduce that to the permissible limit, one way is to add the compression steel to take care of some compression, but that is not what we are looking at this stage. The other way of doing it is increasing the area in compression. What is the area in compression? Area in compression is B times N. So if you want to increase this area in compression, what is the other way of doing it? What is the other way of doing it? How did we determine the neutral axis depth? Neutral axis depth is determined by equating moment of area in compression to moment of area in tension. Okay, moment of area in compression is equated to moment of area in tension. So if you want this compression, if you want the stress in concrete in the extreme fiber to reduce, you need to increase this area. How do I increase compression area? By increasing the area of steel. By increasing the area of steel, we can actually increase the area of compression as well. Okay, but first of all, some amount of area of steel you used, or additional area of steel you used to bring down the stress in the steel, and in addition to that, to reduce the stress in the concrete, again you are trying to increase the area of steel. So the amount of steel, that additional amount of steel that you need to provide to increase the area in compression is going to be much higher. Okay, it's going to be much higher, and it's not actually going to be economical. We'll see that all that in a while. Okay, so let's with that explanation, let's read this. Anyway, these two equations you are familiar with. Okay, so let's read this. In this case, the reduced depth tends to increase both extreme fiber stress in concrete as well as stress in steel. The sigma CBC prime is nothing but extreme fiber stress in concrete. Sigma prime ST is nothing but stress in the tensile steel. A reasonable addition to area of steel would bring actually there is a printing mistake here, would bring this sigma prime st within the allowable. That means you can add some marginal amount of steel to bring down this sigma prime st to its permissible value, but still this sigma prime CBC is going to be very large. Okay, the only way to remedy the over stress in compression, other than providing the compression steel, we are not discussing that at this stage. The only way to remedy the over stress in compression is to increase the compression area by lowering the neutral axis. When you lower the neutral axis, when the neutral axis depth is increased, area in compression is going to increase. How do you bring down the neutral axis depth? How do you lower the neutral axis? This is achieved by increasing area of steel in tension considerably. To bring down the neutral axis, the amount of steel that you need to provide is going to be much higher. Okay, we'll see in an example, then you will get a feel for this. Okay, and so this is basically the concept that is going to be used in over reinforced section. Okay, so now let's take an example, then you will understand better. Okay, so before that, let's note down the what are the equations that are required for solving this. First of all, please note that the beam is shallower than a balance section. So depth is already dictated. Depth is already dictated by the constraints. Width is once depth is dictated, width is also dictated. Okay, width is fixed, depth is fixed, size of the beam is fixed. Now our job is to find the area of steel that is required. Okay, so in this case, the steel is only the only element left to design, because dimensions are fixed because of the constraints, and the total compressive force can be expressed. You know this formula. Total compressive force is half sigma CBC prime times the area in compression, which is B times N. And if you multiply this compressive force with the lever arm distance, which is nothing but JD, or D minus N divided by 3, that is going to be your moment. And you know to what moment this beam has to withstand, or what is the required moment carrying capacity of the beam. M is we are designing the wing, so we know this M. So everything is known here except neutral axis depth. N can be obtained by solving this quadratic equation. This is the quadratic equation. So N neutral axis depth can be obtained by solving this quadratic equation. Once you get the neutral axis depth, you can determine the stress in the steel. Stress in the steel can be determined by these equations, which I told you to make a note. So now the neutral axis depth is known. Extreme fiber stress in concrete is equal to its permissible limit. So you can determine stress in steel. Okay, stress in steel can be determined. Once stress in steel is known, you can calculate area of steel by making use of this stress. Please note that here sigma st is not the permissible stress in steel, but stress in steel when concrete reaches its permissible limit. Okay, so that stress in steel will be using and calculating the area of steel. And once you get this area of steel, and how do you cross check whether this area of steel is correct or not? You can go back to your basics. The neutral axis depth is obtained by taking the moment of area in compression and equating it to moment of area in tension. So using that relation and making use of this area of steel, you once again calculate neutral axis depth and check whether that neutral axis depth is close to what you determined from this first equation. So that is a kind of cross check. Please note that as somebody raised a question yesterday, is B is arbitrary, D is arbitrary. Please, I told you in the beginning of this class itself, in design, if there are 100 students in the class, 100 students can come up with 100 types of designs. 100 students come up with different combinations of D and area of steel, still all these designs or any of these designs can be complying with whatever requirements. Okay, so design is all dependent on individual choice, and also it depends on the constraints. Okay, so you will not be having a unique answer. So you cannot cross-check your result with somebody's results. At each stage, you need to check yourself using a different kind of checks. So neutral axis depth you can obtain once you get this area of steel. Using this area of steel, you obtain the neutral axis depth by equating moment of area in compression to moment of area in tension, and then cross-check whether that neutral axis is matching with this whatever you initially calculated, and if it is matching, then there is no mistake in your design. Okay, so now let's take an example. Before that, any questions here? Any questions? So if there are no questions, let's take the example that we are looking at, that is designing a beam to carry a moment of 150,000 Newton meters. And now let's assume some depth which is smaller than, or which is shallower than, for a balanced section. What is the depth that is adopted for a balanced section? Again, two types of steel, Fe250 and Fe415. For Fe250, if you go back and see, the depth that we provided is, or the depth that we got is 707.2, something like that, 707.2 mm for a balanced section. So here, let's assume that we have some constraints, and our depth is limited to 650 mm. So our depth is lower or smaller than that is required for a balanced section. So let's adopt these dimensions. 250, B is equal to 250, D is equal to 650 mm, and I need to design a beam to withstand this moment, 150,000 Newton meter. Anyway, once the depth is smaller than that is required for a balanced section, obviously it's going to be over reinforced section. If you are not going for compression steel. Okay, so we need to adopt this whatever we just discussed. Total compressive force is given by half sigma CBC. For this problem, we have already noted sigma CBC, permissible stress in concrete, as 7 Newton per mm square, and width of the section is 250, and N is the neutral axis depth, and then this is the moment. Equate the moment to the applied moment and calculate neutral axis depth through this quadratic equation. Please note that in case of under reinforced section, to get the neutral axis depth, we got a cubic equation to solve, whereas here it's only quadratic equation. And then once you get the neutral axis depth, you can also cross check. You can also cross check whether this is actually. Please note that in an over reinforced section, neutral axis depth is going to be lower than that for a balanced section. In over reinforced concrete section, neutral axis depth is going to be lower than that for a balanced section. Lower in the sense the total compression area has to be more, so the neutral N value, N is going to lie below that for a balanced section. For an under reinforced section, neutral axis depth is going to be above the depth of the neutral axis is going to be smaller than that for a balanced section. For under reinforced, for over reinforced, depth of neutral axis is going to be more than that for a balanced section. So you can also cross check that way. Whatever neutral axis depth, you compare it with the balanced section. How do I get the balanced section neutral axis depth? I know the neutral axis depth factor multiplied by this depth, 650 mm. Assuming this to be a balanced section, what would be the neutral axis depth? Neutral axis depth factor, K multiplied by this value You just cross check whatever neutral axis depth that you got is greater than that or not. That is one check, okay? So that check is made here. Once you get neutral axis depth, you can calculate the lever arm distance. Once you get the lever arm distance, we can calculate stress in the steel. Sigma prime ST divided by M is equal to sigma CBC multiplied by D minus N divided by N. And whatever sigma ST prime divided by M, that M can be brought to this side. M is nothing but your modular ratio. You find the stress in steel. Once you get stress in steel, using this stress in steel, you find the area of steel. And once you get this area of steel, one way of comparing this is whatever area of steel that you get here, you can compare with that for a balanced section. Because what we noted, this is an over-reinforced section. Over-reinforced section means area of steel is going to be more than that for a balanced section. So one way of checking that whether this area of steel is making sense or not is compare with balanced section. Suppose if this area of steel, whatever you did calculation, you got some area of steel and it turns out to be less than that for a balanced section, that means there is some mistake somewhere above. So you can cross check your calculations. So this is the area of steel for this over reinforced section. And another way of checking this area of steel, whether it's correct or not, using this area of steel, you calculate neutral axis depth once again. Using this area of steel, you calculate the neutral axis depth. Or what you can do is, you can use this neutral axis depth and get the area of steel. Either way you can do. You can take this area of steel and calculate neutral axis depth and compare with this, or take this value of neutral axis depth and substitute here and back calculate what is the area of steel, and then check whether the area of steel that you get from this equation is closely matching with this or not. So that is what is done here. Area of steel obtained by taking this neutral axis depth is this much, whereas area of steel obtained through stress in steel is this much. So they are in good agreement with each other. Only small difference. Okay. So we can say our calculation is correct. So this is how you will be proceeding with your design. And now same calculation is repeated with Fe415 steel. Fe415 steel, the same calculation is repeated. And also I told you, please see this difference here. For Fe250 steel, what is the area of steel that is required? What is the area of steel that is required for an over reinforced section? That is 2839 mm square. And what is the steel that is required for a balanced section? 1744 mm square. What is the percentage increment in steel? What is the percentage increment in steel? You please tell me quickly. 2839 minus 1744 divided by 1744 multiplied by 100. What is that value?
62.7.
Okay, you make a note of it. So that is the amount of steel we need to use more than that is required for a balanced section. But by using that amount of increase in steel, how much amount of depth we are able to reduce? Percentage of reduction in depth, 707.2 minus 650 divided by 707.2 multiplied by 100. %. Yeah, you can see for 8% decrement in the depth, for 8% decrement in the depth, I need to provide almost 62% increase in the steel. So is it worth doing it or not? That you need to think, because it's not really economical. So that is what is mentioned here. Note, that a 8.1% reduction in D has increased the area of steel by 62.7% compared to that of a balanced section. Okay, so now you got a feel why this I made a statement, or it is mentioned, over reinforced section is expensive. Over reinforced section is expensive because the amount of steel for even small reduction in depth is going to be more. Okay, and similarly you can check for this Fe 415 steel as well. What is the percentage increase in the steel? Please note that here for Fe 415 steel, the steel for over reinforced section is 1303.45 mm square. And if you go back and see for a balanced section, let me show you that. For a balanced section, what is the amount of steel that we got for this steel is 880.15 mm square. 880.15 mm square is the steel that is required for a balanced section if you adopted Fe 415, whereas the steel that is required for this the shallower beam is 1303.45. Okay, so that is the reason why this is called or this is expensive. Any questions here? So we discussed all three types of beams: balanced section, under reinforced section, and also over reinforced section. Another point related to this over reinforced section is, please note that in under reinforced section, steel is going to reach its permissible limit first. In the sense, before concrete reaches its permissible limit, steel reaches its permissible limit. When steel reaches its permissible limit, you will see sagging of beam. You will see noticeable indication that beam is about to fail, or noticeable kind of indications that it's no longer functional. So then you can take care of and then you can actually vacate that. Whereas for over reinforced section, concrete is going to reach its permissible limit first. Concrete is a brittle material. Okay, any material which is in brittle, when it reaches its failure stage, that failure is going to be catastrophic. In the sense, it's going to be sudden failure. So in the sense, over reinforced section may not give that kind of indications which manifest in the form of excessive deflection. Such kind of things you will not be able to see for over reinforced section. So it's not only expensive, but also those kind of warning messages you will not get from an over reinforced section. Okay, any questions? And if there are no questions, we covered three types of sections: under reinforced, balanced section, under reinforced, over reinforced. So now we know how to calculate the area of steel and other things. So once we know the area of steel, we can also express that in terms of percentage of steel. So let's read this, or let's see this: percentage of steel and its effect on moment of resistance. Percentage of steel and its effect on moment of resistance. So once you get area of steel you can express like in this form, or in this form: P is equal to AST divided by BD, or if you want to express P as a percentage, AST divided by BD multiplied by 100. Okay, and we also know this relation: total tensile force is AST times sigma prime ST, and AST, if you substitute in terms of P, it's going to be PBD times sigma prime ST. And so tensile force is percentage of steel multiplied by the cross-sectional area, taking effective depth into account, and then this is stress in steel. And suppose if I adopt the percentage of steel or P value corresponding to that for a balance section. We already noted when we discussed about balance section, I have shown you a table for different grades of concrete, different grades of steel, neutral axis depth factor, lever arm factor, and then the Q balance, resisting moment factor, and also P balance. The P in terms of like AST divided by BD. That for a balance section, I have shown you a table. So let's say we selected some steel and we selected some concrete corresponding to that grade of steel, grade of concrete. We can go to that table and find what is the P balance. So for a balance section, this equation can be written like this: PB multiplied by BD multiplied by sigma ST. And also given for any section, total compressive force should match with total tensile force, and total compressive force is given by half sigma CBC multiplied by B times neutral axis depth, which is KD. So equating this T, whatever this T value, to the compressive force, we can get a relation between P and Q. We already noted this relation. Earlier, we already noted this relation. This is another way of getting it. So PB, once you know the percentage of steel for a balance section, and that is related to resisting moment factor and the permissible stress in steel and the lever arm factor. Okay. So now let's see the moment of resistance, how the moment of resistance or M, how M varies as the percentage of steel is changing. Okay. Instead of M, usually we express it as M divided by BD square. What is M divided by BD square? It's nothing but resisting moment factor. M divided by BD square is nothing but resisting moment factor. So we will see a plot with vertical axis M divided by BD square. On the horizontal axis, we'll see the percentage of steel. So this is how that plot looks like. As the percentage of steel is varied, how the moment of resistance is varying. Moment of resistance is normalized here, or it is nothing but Q, resisting moment factor. And this plot is showing for two types of steels. Okay, one is for Fe250 steel, this solid line, this black line or black solid line is for Fe250 steel, and this dotted line here is for Fe415 steel. Fe415 steel. Okay, and the point I want to bring to your attention is, anyway, this is for two types of steels, Fe250 and Fe415 steel, and the grade of concrete is same. Grade of concrete is the permissible stress in concrete is 5. So if you make use of these values, you will be able to reproduce this curve. Anyway, the point I want to show to you is, and this you can see here, one of the curve. Let's see this solid line. As the percentage of steel is increasing, resisting moment factor or moment of resistance is increasing, and up to certain point, the increase in the percentage of steel, increase in the moment of resistance or resisting moment factor is proportional. It is changing in a proportional manner. Okay, or the increase in the resisting moment factor or moment of resistance is very sharp up to certain point. Okay, up to certain point it is very sharp, and beyond that point, the increase in the moment of resistance is not that that steeper when compared to the increase in the area of steel. And this point like on this plot, up to the point where this increase in the resisting moment with respect to the percentage of steel, that proportionality is maintained. That is nothing but your that value corresponds to your balanced section. That value corresponds to your balanced section. Okay, let's see this. Let's see whether this is correct or not. So let me go to the table. Sigma CBC is 5. Sigma CBC is 5. Sigma ST is 140. Corresponding to that, let's note down what is Q balance. Okay, so let's go to the table. Sigma CBC is 5 and sigma ST is 140. And what is the balance? Q balance 0.874. Okay, or you can round it off and then you can say 0.8. Okay, or sorry, not this one, sorry, this is Q balance, that is 0.874. You note down these values, please note down these values, then we'll go to that plot once again. Sigma CBC is 5, sigma ST is 140, Q balance is 0.874, P balance is 0.2072. You make a note of this. So this is the type of steel and this is a type of concrete we are using. Also note down this one. Also note down for Fe 415 steel. Sigma ST is 230 and Q balance is 0.659 and P balance is 0.2032. You please make a note of these two. Okay. So whatever plot we are looking at is the moment of resistance versus the percentage of steel. So the point I'm mentioning is the proportionality is going to be maintained. The proportional increase in the moment of resistance as you increase the percentage of steel is going to be maintained up to this value of percentage of steel. If you are using this Fe 250 steel, this is nothing but 0.8. You can say 0.8 or 0.7%. Okay, 0.8 or 0.7%, and here it is 0.3%. So let's see that plot. Here you can see here it's maintained, the proportionality is maintained up to this, then that corresponds to 0.8, and similarly this corresponds to that 0.3%. Is it clear? And beyond this proportionality point, the steepness is reduced, or the increase in the moment of resistance with respect to the percentage of steel is not that much. And this transition point, or the point where the behavior is changing, that is corresponding to balance section. And whatever portion is there below this point, that is under reinforced, and whatever portion is there, that is over reinforced. So what is the inference that you are getting from this? The inference that you are getting from this plot, it's not that as you keep on increasing the percentage of steel, your strength is going to increase. Okay, the strength is not going to increase, or it's not worth putting more amount of steel thinking that the moment of resistance is going to increase. Okay, so that is what is actually this figure is representing that, and that is what is mentioned here. For values of P smaller than that, for a balance, the percent, P is nothing but percentage of steel, smaller than that for a balanced section. Okay, PB. Just now you noted PB for sigma CBC equal to 5 and sigma ST is equal to 140. PB is 0.2072 or 0.2081. and for Fe415 steel it is 0.2032. Okay. For values of P smaller than PB, section becomes under reinforced, and for values larger than PB, the section becomes over reinforced. Any questions here? Professor Amlan, you want to add something?
No, this is an important graph, just to appreciate that there is no benefit of going for over reinforced in terms of economics. And later on, when we go to the limit states method, we will see that the code actually does not allow us over reinforced. It enforces under reinforced. Okay.
No questions? You should have some question here. Something I have not explained. Something I have not explained in this plot. Can you figure out what it is? You need to be more attentive. Understand, I have not explained to you what is this P min here. This P min is nothing but code is, you need to go back to your IS 456, page 47, IS 456. Code is giving you what is the minimum area of tension reinforcement. Read this: minimum area of tension reinforcement shall not be less than that given by the following equation. Shall not be less than that given by the following equation. What is that equation? AST divided by BD, or it is here instead of AST, it is written as AS. That is having same meaning. AS divided by BD is equal to 0.8 divided by Fy. And again, please note that this equation is, you can say it's an empirical equation, and you need to take it as 0.85, and Fy you need to substitute in terms of Newton per mm square, MPa. Fy is in MPa and 0.85. So 0.85 divided by 140. What is that value? 0.85 divided by 140. And also 0.85 divided by 230. What is that value? Two values, you tell me. Nobody is answering. Quickly. 0.85 divided by 140. 0.85 divided by 230.
.006 for first one.
First one. That corresponds to this. That corresponds to this. Sorry, that corresponds to this one. This point corresponds to 0.85 divided by 140, and this point corresponds to 0.85 divided by 230. Okay. So I'll stop in a few minutes. Before that, let me summarize. Let me summarize what we have studied or understood. We noted what is a balanced section. We noted what is under reinforced, what is over reinforced. Okay, and we also noted the procedure for getting the area of steel once the dimensions are fixed. So now let's summarize that. Let's summarize that. Whatever we understood, that is what is summarized in this table. So this is like a summary of what you have studied in the last two classes. Once the dimensions of the size of the section is known, how to get the area of steel. So you can read, whatever equations you noted, all those equations are put together here. Okay. So if it is under reinforced section, under reinforced section, the moment carrying capacity or the actual moment is going to be less than whatever. Once you have the grade of concrete, grade of steel, you can go to the table just now, whatever we have seen. you find Q value and P value from there, and using that Q value, the actual moment is going to be less than the Q value multiplied by BD square, and the same equation can be written in this manner. Okay, or the one way of checking is actual moment of resistance is going to be less than that for a balanced section for the same dimensions, and then or the moment resisting factor is going to be less than for a balanced section, or the depth is going to be more than that is required for a balanced section, and the actual amount of steel that you provided is going to be less than that for a balanced section, and the neutral axis depth is going to be less than that for a balanced section, and the stress, extreme fiber stress in concrete is going to be less than that for than the permissible stress in concrete, and also the steel is going to reach its permissible limit, and the stress in concrete, in the extreme fiber stress in concrete, can be calculated using this equation, and substituting this equation into the relation connecting the moment with the compressive force, you can determine the neutral axis depth, which involves solving cubical equation. Once you get the neutral axis depth, you can calculate area of steel, and also area of steel you can use also approximate method. Okay, so whatever we covered in yesterday's class, that is summarized here. And also this is for a balanced section. This is all self-explanatory. Actual moment of resistance is going to be given by QBD square, and then you can rearrange this. Q value is going to be same as for a balance Q, and actual depth is going to match with this, and all this actual P, percentage of steel, is going to be same as what is shown in the table, and this neutral axis depth is going to be matching with balance section neutral axis depth, and steel concrete is going to reach its permissible limit, as well as steel is going to reach its permissible limit, and moment is related to this dimensions through this relation. M is equal to QBD square, and area of steel can be obtained like this. AST is equal to M divided by sigma STG. And if it is over reinforced section, actual moment of resistance is going to be more than that for a balanced section for the same dimensions. Please note that here I am saying it's for the same dimensions, or this can be written in this manner. Resisting moment factor is going to be more than that for a balanced section resisting moment factor, or the depth, actual depth of under over reinforced section is going to be less than that for a balanced section, and the percentage of steel that you provide is going to be more than for a balanced section, and the neutral axis depth is going to be more than for a balanced section, and concrete is going to reach its permissible limit first, and the stress in steel is going to be less than the permissible stress in steel, and the neutral axis depth factor or neutral axis depth is obtained by equating moment to the moment of compressive force, which results in a quadratic equation. And once you get the neutral axis depth, stress in steel can be determined using this relation. Once stress in steel is known, area of steel can be obtained using this. Okay, so this summarizes everything what we covered in the last two classes, and I have given you assignment 3. Whoever already solved assignment 2, then they can start assignment 3. Assignment 3, first 3 problems are analysis problems, which are based on what is covered, and 4 and 5 problems in assignment 3 can be solved using this table, using the information that is summarized in this table. Okay, and we'll discuss further in tomorrow's class. And who have not submitted assignment, you need to submit. Otherwise, please note that your assignments are going to pile up. Okay,
Sir.
Professor Ramlan, you want to add something or any other questions?
Sir, in the assignment, what do you mean by check the adequacy of that statement?
Check the adequacy in the sense you need to check whether the moment carrying capacity is matching with moment of resistance of the section.
Okay, sir.
Sir, but we have not been provided with the grades of concrete and the steel.
Huh? Grades of concrete and steel are provided.
Yes, sir, in the question.
So let me just show you or see that. 1 second. 1 second, don't go away. Which one? Here, this one. Okay, first question. Please note that you are doing design. Okay, you are doing design. So you need to if some information is missing, you assume that and then proceed with the problem. Okay. So in the first, the question is in the first problem, grade of concrete is not given, grade of steel is not given. You adopt same as what is given in the second problem. Please note that in design, you don't need to complain about something which is missing. If something is missing, you can use or you can assume reasonable values. But only thing is whatever you assumed, you need to clearly mention that. Okay. So these problems, these two problems also you should be able to solve. 4 and 5. Okay. Professor Amlan, you want to add something? Students are leaving.
No, I think for today it is okay.
Okay, thank you very much.